Welcome back to Astronomy Untitled Seattle. Our first speaker tonight is a PhD student who just gave her dissertation talk at the AAS. Please hear it for soon-to-be Dr. Yvette Cendes.
No pressure. All right, hi everyone, Astronomer here. I am here to tell you guys a bit about what I do and just sort of a cool story about the cosmos that will hopefully affect all of our lives someday. So I'm going to talk to you guys about supernovae and what would happen if a supernova happened in our own galaxy and its light reached us tonight. What could you expect? So, to start off this little tale of ours, if it is winter and you're looking up in the night sky looking south, so if it's theoretically not cloudy in Seattle, these are stars. And in the night sky, in the winter, I really like it because we have Orion. Orion's a very cool constellation because I think it actually looks like something unlike some other constellations. So first here we have Orion's belt. Some of you guys might know this. The three bright stars here make up Orion's belt. Part of the entire constellation of... Where did I point it? Guys, where did I point it? Ah, okay. Thank you. Orion is the constellation here. And Betelgeuse is the bright star up here. You guys can wait a second? Yeah, okay. Betelgeuse is a very bright red star, makes up the left shoulder of Orion. Rigel is the star down here, another bright star in Orion. And the cool thing also about Orion is if you follow the belt down, you get to the star Sirius. That's the brightest star in the night sky. Orion's also cool, because if you're looking here at Betelgeuse, this sort of reddish star, the left shoulder star in Orion, that is a star that astronomers think is at the end of its life and is going to go supernova someday. So, the thing to also remember about stars is just because we see them in the night sky doesn't mean some are closer, some are further. They're all vastly different sizes. So, if we're looking at a few of the stars that I was just showing you in the night sky, so here's our sun. It is a very tiny star compared to stars like Sirius. Okay, Sirius is definitely bigger. Rigel is huge. Betelgeuse is the biggest of all. The reason this happens is so if you're a star like our sun, when you reach the end of your life, so 99% of stars, you kind of swell up and you poof out your outer layers, and then that is the end of your stellar story. If you are a star, however, big like Betelgeuse, what is going to happen is you are going to swell up. You're going to be huge, absolutely giant. And what is going to happen, though, at the end of your stellar life, when you finally run out of fuel at the center of your core, is you are going to end up in a supernova explosion. So when a supernova explosion happens, the stars basically run out of fuel at the center of its core, and basically the outer layers come down, a neutron star or black hole is formed in the center, and we have basically an explosion that is the biggest explosion we really know of in astronomy. One supernova can be brighter than the light of the rest of the galaxy when you see a supernova occur. So these things, you can see them from even billions of light years away, for particularly bright ones. And the thing about supernovae is we actually know about them pretty well, and the reason is, trust me, supernovae are cool. Sorry, guys. There we go. Oh, there we go. Anyway, sorry. Thank you. Apologies, guys. We have that, and now we're going through all of my slides. Okay, let's go back here a second. Anyway, okay, so supernova. The reason we know about supernovae is what they would actually look like for us if they go up in our own sky. Is we've actually seen them. We have them in the historic record. Chinese astronomers in particular were very good about recording the guest stars in the sky that they saw. So stars that suddenly showed up, that were suddenly bright, and you could see. So supernova 1054 AD is a particularly famous one. And the reason is, if this was a supernova, the Chinese, the Japanese, the Arabic astronomers definitely saw it. We also think that European and astronomers in Chaco Canyon, so people all around the world saw this object. The reason was it was so bright you could read by the light of this star. It was so bright, it was in the sky for 2 years as a guest star. They had no idea, of course, what was causing it. But it turns out, because the Chinese astronomers are very good at recording where these guest stars are, we can go today and see what exactly is in that location. And if I can figure out where the magic point is. Ah! Okay. What? No. Yeah, here we are. So this is what you see at the point of 10:54. How about I just tell you next slide? Is that okay? And then you just
sure. Yeah, let me see if that
thank you. So this is what you see. That if you go with the Hubble telescope, you see this thing. It's called the track nebula. So next slide, please. So the thing about supernovae, though, is, as I said, 1054 we don't actually see them that often, and the reason is because, as I said, only 1% of these stars go to supernova. So we end up having effectively one supernova in a galaxy our size per century. So when that happens, the last time we saw one in our own galaxy was 1604. Galileo saw it. He didn't have his telescope yet, so he couldn't point it. But 1604, I just told you one every century. Well, we have a lot of dust in our galaxy. Probably a few supernovae have happened, but we just have not seen them because of the dust between us and it. So the closest supernova to us since the invention of the telescope is this object here called Supernova 1987A. And the reason I like Supernova 1987A is it's actually one of the things I talked about in my PhD thesis. This is part of what I do my research on. And it's also one that tells you, like, when I tell you what we will see for a supernova in our own galaxy, this is what we're really referring to for a lot of the information. First, it happened not in our own galaxy. It happened in a galaxy called the Large Magellanic Cloud, which is a satellite to our own. It's basically 170,000 light years away, but you can look out of the galactic plane, so that's why we can actually see a lot of cool things happen in the Large Magellanic Cloud. And you could, even though it was so far away, if you're in the southern hemisphere, briefly see it for a few weeks with your naked eyes. That's pretty cool. Next slide, please. So what I do, if this little GIF here works, yes, so I basically study this supernova when the shockwave happened. The shockwave goes out and interacts with all the material that is surrounding the region of 1987A that the star ejected before it died. So if you want to know what happens in supernovae, it's a bit more circular, but normally, but you can basically see this region light up, and you can see the supernovae. They really also interact with the surrounding galaxies, the surrounding systems. A lot of star formation gets triggered as the supernova shock waves go out, and then you get, as I showed you that picture of the supernova room that's left over later. This is all radio data, by the way. This is why I'm very radio strong here as a person. Anyway. So to sort of wrap up, though, so like what would happen if this supernova, though, happened closer than the Large Magellanic Cloud? Let's consider this for a second. So first of all, so the first thing to emphasize is, okay. So we're not going to die. This is the first thing often people worry about whenever you talk about giant explosions in space. And we're not going to die if a supernova happens in our galaxy. Why do I say this? So if a supernova is going to disrupt our atmosphere and things like that, it has to be within a few hundred light years up to maybe 1,000 light years maximum. These stars, I mean, Betelgeuse, that was a huge star. You can see that from very far away. We're pretty sure we know about the immediate area around us, and we don't see any stars that are about to go explode that are going to really hurt us. So that's cool. So next slide, please. The next trick, though, is okay, what kind of alert will we get if there's a supernova? Some of you guys might say nothing goes faster than the speed of light. That's not quite true in the case of supernova. There's a little technicality here. There's these little particles in the universe called neutrinos. And neutrinos are fundamental particles. They're like electrons or, all of your other favorite friends like that. But they're a little different because there's just a bunch of them. So this is an interactive astronomy on tap. Everybody give me a thumbs up. Hey! Okay, so when you do your thumbs up, every single second, about 1 billion neutrinos go through the tip of your thumb. So these are particles. They are just very weakly interacting. They don't really interact with anything. But when a supernova happens and that neutron star is created in the center of the supernova, basically enough neutrinos come out. It's about the number of atoms there are in the sun. And what happened for 1987A is detectors like this. This is a neutrino detector. Just for comparison, next slide, please. If you look, that's two people in a boat for comparison of what this neutrino detector is like in size. And the first time we ever detected neutrinos from outside of our own galaxy was or from our own solar system, forgive me, was actually during 1987A. I told you all these neutrinos get created, and they saw like 20 at 3 observatories around the world, and it was the coolest thing that ever happened in neutrino astronomy to that date. So, but the trick is also, if you get, the neutrinos arrive a few hours before the light, because I just told you they don't interact with anything. The light has to travel through the layers of the star when the core of the star collapses. So you actually get the alert from the neutrino stream several hours before the actual supernova event is seen. You can actually, by the way, go online. There's a Supernova Alert network, neutrino network, that you can sign up for alerts. If suddenly all the neutrino detectors around the world go off, you can sign up to say, okay, like, I want to see what's going to happen. So, with that, what's going to happen, next slide, is, so if you go out, and, you know, we all received the alert tonight, we're going to run outside and hope it's clear, and we're going to go out, and we're going to see this view here. And the next slide, please. So what is going to happen? You're going to stand there. Maybe you're going to be the first person in over 400 years to see light from a supernova in our own galaxy. And you're going to wait. And you're going to wait. And you're going to be like, oh, maybe. Love astronomy is waiting. And then look, there we are. And then that is what it will be like. Suddenly we'll have a guest star for the first time in hundreds of years in our own night sky. And that is what will happen if we have a supernova in our own galaxy. Thank you very much.
We have time for questions.
So the question was, do all stars supernova? No. So only 1% of stars are massive enough to go supernova. You have to be roughly 8 times the mass of our own sun to go supernova.
How did you know the 1987 star A was the cause of the neutrinos versus just other neutrinos in the galaxy?
So in the case of supernova 1987A, basically because there was the supernova event and they knew from theory that that's what caused it, and they literally never detected neutrinos before, that was the main reason for it. But as I said, it was also the fact that it was a few hours before the light. So the question was, where is the picture of the neutrino lab? That was actually in Japan. So the Japanese are very good at neutrino astronomy. It's one of their leading things in astronomy.
Could you use the various neutrino detectors as kind of triangulation as a big telescope to point you at the supernova?
So the question was, can you use the neutrino detectors as a telescope? So the answer is, people can now, the field's had 30 years or so to evolve. And the field is now at the point where, yes, you can, they have actually, within the past year, at the first time where there was a blazar, so a black hole that was very energetic, and associate neutrinos with that. In the 1980s, though, that was a bit beyond their technology. So the question was, that's a good question, how do you validate data from 1000 AD? I think the fact that if you go and then you see the supernova remnant there is very telling. And also the fact that all of these records were within a very, the same period of time. But yeah, archaeoastronomy is a thing. So supernova remnant is literally just the remnant of the star and the gas and everything surrounding it. Yes. Sorry? So supernova remnants, that's its own field of astronomy, and yes, so, yeah. Okay.
We've seen light from the supernova. Have we detected gravitational waves from them?
Okay, so the question was, it's a good question, have we detected gravitational waves from supernova? The answer is no, but my understanding is when this supernova goes off in our own galaxy, LIGO should be able to detect it. I did actually ask at one point, for whatever basic gravitational wave detectors there were in 1987, did they detect it or not? Apparently there was a conference and everything was turned off that week, so we actually... So So that was a good question. Is there another star that might go supernova other than Betelgeuse? Actually, the best candidate, in my opinion, is the star called Eta Carina, but it's in the southern hemisphere, so the talk is not as good. You know, if I do that. But that star is also very close to the end of its life, so you might have to buy a ticket south to see the guest star. All right, thanks, guys.
Let's hear it for him.